Yeah, very good morning. Myself, K. Bhaskaran. I am working as a assistant professor in Covenant College of Engineering and Technology. I am going to take the project. I am going to take the subject of this bio MEMS. Before we are going to see that this what is meant by MEMS. MEMS is a micro electromechanical system. In this first unit, we are going to see the materials and the fabrications. What are the basic materials that we are required for the making the device, and how we are doing that is manufacturing, that is fabrication process. This basically MEMS technology consists of microelectronics elements, actuators, sensors, and mechanical structures built onto a substrate, which is usually silicon. They are developed using microfabrication techniques. There is different types of techniques they are used in the MEMS. That is deposition, patterning, and edging. The most common forms of production for MEMS are bulk micromeasuring, surface micromeasuring, and a high aspect ratio. That means high HAR fabrication. The benefits on this small scale integration brings the technology to a vast number and a variety of devices. Basically, in the first unit, we are covering that is what are the MEMS, materials of MEMS, and components of MEMS, and fabrication, MEMS operations, applications. We are going to see these are the outline of the first unit. This is a basic examples of that there is MEMS, that is micro electromechanical system is the integration of mechanical elements, sensors, actuators, and the electronics on the common silicon substrate through microfabrication technology. These are the basic things we need to do there is basic requirements for making the MEMS devices. So water made up of components between the ranges between the 1 to 100 micrometers in size. Devices vary from below 1 micro up to several millimeter. Functional elements of MEMS are miniaturized structures, sensors, actuators, and microelectronics. One main criterion of MEMS is that there are at least some elements that have mechanical functionality, whether or not they can move. That is basically that is MEMS is that is categorized microsensors, microactuators, microelectronics, then microstructures. In this microelectronics, brain that receives, processes, and makes decisions, data comes from microsensors. That is, microsensors constantly gather the data from the environment, pass data to the microelectronics for processing, can monitor mechanical, thermal, biological, chemical readings. Microactuators act as a trigger to activate that is external device. Microelectronics will tell microactuator to activate device. Microstructures, extremely small structures built onto a surface of chip built right into silicon of MEMS. Activate substrate materials. Activate substrate materials are primarily used for the sensors and actuators in microsystems. Typical materials silicon, gallium arsenide, germanium, and quartz. All are that is basically that is a semiconductor except that is quartz. Have a cubic crystal lattice with threaded atomic bond. It by having that atomic bond, threaded atomic bond. Reason for activate substrate materials, dimensional stability, intensive to environmental conditions. A critical requirement for sensors and actuators with high precision. Each atom carries four electrons in the outer orbit and share these four electrons with its four neighbors. In the silicon substrate, silicon crystal be single crystal silicon is the most widely used substrate material for MEMS and microsystems. The reasons are that it is mechanically stable and can be integrated with electronics for single transaction on the same substrate. High young modules and light weighted, high melting point at 1400 degrees Celsius, low thermal expansion coefficients, no mechanical diseases. These are the basic requirements we are selecting the single crystal silicon for making the substrate. There is a properties of next we are going to see. There is a properties of gallium arsenide and a silicon substrate and quartz. In this section, we had to gallium arsenide and silicon substrate quartz. These are the basic properties we recording on this unit. These are the basic requirements. There is basic properties, formula weight, crystal structure, lattice constant, melting point, density, thermal conductivity, band gap, intrinsic carrier concentration, intrinsic resistivity, breakdown field, minority carrier lifetime, mobility. These are the basic properties of the gallium arsenide and the silicon. There will be a little bit different between there is gallium arsenide and silicon. Compare the gallium arsenide, there is silicon is the best substrate we are using that in the silicon. This MEMS technology, we will be choosing that. When we are going further, there is fabrication technology. There is we have to do there is deposition, etching, and patterning. In this deposition, there is chemical vapor deposition, physical vapor deposition, epitaxy, oxidation, evaporating, sputtering, spin on methods. In etching, we have two types. There is petrochemical etching, dry etching. In wet etching, there is isotropic, anisotropic, and non-isotropic. There is three methods are available. In dry etching, there is plasma etch, reactive ion etch, patterning, photolithography, X-ray lithography. There are two types of patternings we are having that in this in this in this fabrication technology. This is the sputter deposition. This sputter deposition is used for making that is a thin layer in the that is a substrate. We are using the different types of deposition. First one is sputter deposition. The next one is magneton deposition. The next one is ion beam deposition. These are the when we are using the sputter deposition, we are having some advantages and disadvantages. When we go for move for that next unit, that is mechanical and thermal sensors and actuators. In this unit, outline of these thermal sensors and actuators, static bending of thin plates, mechanical vibration analysis, thermomechanical analysis, fracture mechanics analysis, thin film mechanics, overview, finite element analysis. Mechanics for MEMS designs, there are three-dimensional structures that are often involved in that transmission as well as solid fluid interactions. The most MEMS components are microscale machine components. Example, this gas, springs, and bearings linkages. MEMS is divided in three types of mechanisms: solid mechanisms, fluid mechanisms, thermomechanics. The other solid mechanics are frequently applied in the design and the operations of accelerometer, process sensors, etc. Fluid mechanics is involved in the design of microvalves and microfluidics. Thermomechanics is used to study the stress state in MEMS components and discerning the temperature field in MEMS structure. This is the solid mechanics structures that is static bending of thin plates. The thin plate thickness is much smaller than its plane dimensions B and C, that is T less than that is B or C. This is a differential slice cut in that thin plate, that is in this thin plate. Mechanical vibration, elementary parts of the vibrating system. The elements that consist of a variety of that is consists of vibrating systems are illustrated. They are idealized and called the mass, the spring, the damper, and the excitation. The first three elements describe the physical system. This is the periodic motions when you are using that is displacement. Many physical systems are essentially discrete systems. The concepts can be extended to analyze the vibration continuous systems. Many physical systems are too complex to be investigated analytically as elastic bodies. These are often studied through the use of their equivalent discrete systems. The assumptions of lumped parameters is not to replace the basic understanding of a problem, but it is simplifies the analytical efforts and renders a techniques for the computer solutions. This is the rectilinear and rotational. When we compare the systems, we are having the rectilinear system and a rotational system. Spring force is spring torque, and the damping force, damping torque, inertia force, inertia torque. These are the examples of vibrating systems. The spring would be a linear spring. Mechanical vibrations analysis. Mechanical vibrations principle is used to design of micro accelerometer, which is a common MEMS device for measuring the force induced by moving devices. Micro accelerometers are used as sensors in automobile airbag deployment systems. We will outline some key equations involved in that micromechanical vibration analysis and show how they can be used micro accelerometer design. Fraction and thin film mechanics. In this fraction, I will be using that. We are making that substrate. We will be making some fraction will be occurred in that substrate material. So we are going to remove that the fraction. At the same time, we are going to remove that crack as well as where the crack is removed. That is based on that some substrate coating. This the crack driving force and the crack resistance will be looking like this. It will be appeared in the 10 micrometer. Case 1, the initial flash size is much smaller than the film thickness. Case B, the initial flash size is comparable to the film thickness. These are mechanical sensors and actuators. This diagram is shown in that mechanical sensor and actuators will be fixed in that cantilever between two ends. Microplate strains and process will be occurred in that mechanical sensors and actuators. Objective of the cantilever beam, that is cantilever beam very most important in the MEMS design because of we are without cantilever we can't able to make the mechanical device can't attached with that is microelectronic devices. They'll be they'll be used in that mechanical devices. Disadvantages, that is a cantilever. These are the examples of the cantilever. Some that is advantages are used in the cantilever. There is a microplates, and I'll move further to microplates. Microplates will be most important vital role in that MEMS design because of microplates will be used in each and every device manufacturing. When we go for the flow measurement, there is a orifice and ventilator flow meter, rotometer, and ultrasonic flow meter. There will be three types of different flow meter we have studied here. Thermal sensors and actuators will be used. Thermal sensor will be used to measure the thermal. Then will be called as the temperature sensor will be called with this sacrificial layer will be looking like this. The thermoelectronic microplates of AFM temperature sensors. This is sensors shape. Next, we go for this unit is the shape memory alloy. SMEF would be used to for that are materials that can be deformed on temperature, but when heated or cooled, return to their original shape. The alloy appears to have a memory. Strains up to about 10% can be fully recovered. Alloy that exhibits this happen only when heated are said to have a one-way shape memory. This transformation sequence is illustrated in below. These are the superelasticity shape memory. In the superelasticity will be appear in that shape memory alloys. Applications of these are the applications of shape memory alloy. Next, then the temperature.